Well, I think we can get going. Welcome back, folks. Kind of a small class today, but we'll make the best of it for sure. Big announcements are we got through our very first exam, so congratulations on that. And pretty much how the Canvas course page is going to proceed from here on out is just basically a redo of everything from week one. So we're starting over in a certain sense, including section 1.5 from last Thursday. We'll have a normal week on week five, normal week on week six, sort of a normal week on week six. On this week six, this is where I'm going to start to transition to putting new information down here on week eight about the content on exam two, sample exam problems. And I'll also be contacting everyone in the class about the testing centers to get everything scheduled. Then week seven will be kind of a normal week, and we'll be back at it on our second exam. So everything that happens on the Canvas course page, the way things get posted in, moved around, the way material pops up for the review on the exams, all just kind of duplicates over and over again. Let me go back to where this is at. There we go. As far as exam one went for the summary statistics, average came out to 84.2%, and the maximum obtained was 100% on this exam. It was kind of a short exam. I think people in person in the class got done somewhere around the half-hour mark. Wasn't a lot of sections, so that was probably the major reason for that. But for the upcoming exams, I'm not going to try to take that as a call to double the length of the exam. It's going to be about the same amount of questions on the future exams. It might be longer exams just because some of the questions get a little more computational. 1.5 didn't quite make it, but putting something as a solution set in parametric vector form, that would have been a longer problem that probably would have extended the length of the exam, for example. But any questions, folks, about the exam or anything at the moment? Okay, well, if you're in the in-person section and I don't have an opportunity to hand it back to you today, then feel free to contact me. I'm happy to send out a scan. And I can definitely, if you're coming into class a little bit later, I'll hand you one back right at the end of class. For everyone that took the exam in the various testing centers in the online section, see your ISU email if you haven't already. I just directly emailed to you in a new email your graded exam. And after all exams are graded, I'll always post the solutions so you can take a look at that document as well. If you have any questions, don't hesitate to write or pop in during office hours. I'll be happy to help out. But for now, we're returning to section 1.7. We did one example in that section after finishing off 1.5. Here we're looking into linear independence. And for the next topic coming back on Thursday, maybe early start on this one as well, we'll be looking into linear transformations. The video here is a great kind of guide on some applications to computer graphics on linear transformations. Things like rotations, skewing, translations, and such is all covered here. And kind of the idea of what's going to happen in section 1.8 is we're just going to look into what we mean by a matrix times a column vector, look at it from a different point of view of really we're just defining a function when we're doing that. A particular kind of function which we'll call linear. But in a very specific sense, we mean linear, not y equals mx plus b, for example. Other optional videos here are kind of a recap of content we've seen already. A little bit less of a recap on this one with linear transformations. So you might want to take a look into these ones just to see linear algebra from a different point of view. This author, 3 Blue, 1 Brown on YouTube is really, really good at computer graphics and has a way of just taking these kind of topics in linear algebra and other subjects and make them really easy to understand visually. The whole series is great, but these are probably 2 videos you'd want to take a look at into. So we'll jump back to example 2 next, but any questions so far, folks, before we get started? Okay, so here's where we left off. Working through this big definition here. Let's do a recap since it's been a whole weekend. We say a set of vectors, v1 through vp, in a vector space Rn, is linearly independent as a set if the vector equation it has only the trivial solution. Vector equation could be rewritten as a matrix equation, but this is the prototypical way to define it because we change the vector space to something else, something more exotic, we don't necessarily have the matrix equation we would like. So this is what the core definition really looks like. Linear dependence means in place of x1, x2 through xp, we've put c1, c2 through cp. If we can find a set of numbers that are not all zero, meaning we have a non-trivial solution, we say that the set of vectors is linearly dependent. And the values that we put down here, we call a dependence relation. So a quick run through of these ideas so far was the zero vector was linearly dependent because when we run it through this equation right here, we found a non-trivial solution. x1 times z, if you pick x1 equals 2 here or here, for example, we still satisfy the equation x1 times z equals 0. So because we found a set of scalars, c1 equals 2, for example, certainly it was not 0, we have linear dependence. Then when we turn that all around, if we have one vector, but it's a non-zero vector, and we take, say, x1 times that vector v, working through the vector equation here, we equated all of the entries to 0. This told us x1 has to be 0 if we take this equation, x1 times v equals 0. That means there was only the trivial solution, and that set of vectors containing just v was linearly independent. So far, this is what we know just through examples, that if you're considering just a single vector in a set, it's kind of a boring set, but we can absolutely do that. We have linear independence if and only if it's not a zero vector. That means linear dependence would occur if and only if it is the zero vector. There's a lot of theorems that we're going to take a look at in this section, and a lot of them depend on how many vectors you're looking at a single time. If it's just one vector, then this is a great way to go. And next, we're going to look at two vectors at a single time. Any questions, folks, with our recap so far? Okay, so we want to extend onto this. One vector has a particular nice theorem for determining independence versus dependence. And so does two vectors. These are the ones that we would often do without row reduction. And so here's our next example. We wonder if these two vectors are linearly independent. Like before, it's kind of a tough question just staring at it all on its own. So we view it under the lens of what is the definition. We write down a vector equation, so we could call this one v1, this second vector v2. Let's match this up just to learn the definition. We write x1 v1 plus x2 v2 equals the zero vector, and see if we can get a solution to this. But you know, the more you stare at these two vectors, there's something particular about them. Notice if you multiply entry 1 by -2, you get entry 1 of the second vector. Multiply by -2 here in the first vector on the second entry, you get the correct second entry on the second vector. This means these are non-zero multiples of each other. Let's write down that dependence relation. 2v1, let me try again, -2v1 is equal to v2. They're non-zero multiples of each other. Let me write just for short. Multiples of each other. That means if we want to resurrect the 0 on the right-hand side in our vector equation, just subtract v2. -2v1 minus v2 is now equal to the 0 vector. Or if we wanted to write it in a different form, let's do that just for the sake of variety. We could have written it this way as opposed to how it's written by the red dot. But this gave us two scalars, -2, -1, which can go here and here, satisfying the equation. So we have a non-trivial solution x. If we wrote it as just a single vector, then it would have components x1, x2, set equal to -2, -1. It's definitely not trivial because this is not the zero vector itself. And then automatically tells us something about these vectors. We found a non-trivial solution, so they are automatically linearly independent. So let's write that here. Therefore, the set V1, V2, we think of this as a set, so we don't say are linearly dependent. We just think of this as the singular one set is linearly dependent. Well, any questions, folks, about the linear dependence on this one? Okay, looking at this from a slightly different point of view, let's add just an optional visual on this one. If we plotted V1 on the X1, X2 plane in this way, this would be at 1, 2, negative 1, 2, 3. So here's V2. And if we did something additional to this, let's look at the span of V2. Span of V2 is all linear combinations. But because that's just one vector, that's also said as all multiples of the vector V2, including the zero multiple, which is just the zero vector down here. So this arrow represents span V2. Or excuse me, V1 is the one I was trying to plot. Let me fix my subscripts here. V1 goes to negative 3, so that's a V1, and that's a V1 there. V2 is the one that goes negative 4, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And my graphing is not perfect. I don't have good grid paper. But if I graphed this perfectly, it would have landed right here inside the span. And it's not a coincidence here. If I have two vectors in the span of the same set, if they lie on the same line in the X1, X2 plane, that's another reason we're seeing linear dependence in this case. So this idea, again, only works for two vectors. It gets more complicated if there are three at a time. But we'll look at a part B when there is linear independence and see how to show it, see how the graph might compare as well, just to get a geometric intuition on this. So here's the next set of vectors. We might wonder, would this trick work again? Can we find that they're multiples of each other? And just a really quick visual experiment will tell you probably not, right? Because the only way they're multiples of each other is if I multiply entry 1 here by 10 to get the 10 here. That's the only thing I can do. But then I'm scaling the whole vector by 10, so I have to multiply entry 2 here by 10, and we would have gotten 50. So if that second vector is 10, 50, they're automatically linearly dependent. That's not the case, so we're expecting linear independence on this one. Let's do the y on this, because that's kind of part of the fun. Well, part of the major thing we're trying to do is really learn the definition itself. So let's repeat our same approach. Call this vector v1, this vector v2. We'll consider the vector equation written in this form. x1 v1 plus x2 v2 set equal to the zero vector. Now, I don't have any tricks this time because they are not multiples of each other, but we can look at this from a different point of view. The matrix equation would have looked like this: 1, 5, 10, 0, x1, x2 equals to the zero vector. And now we have some options on this. We could consider the augmented matrix, augmented with 0, 0, or we could just consider the matrix alone. We know a lot of interesting theorems about this. Let's rewrite this as the form ax equals a zero vector, where a is this vector, 1, 5, 10, 0. There are non-trivial solutions to the vector equation, non-trivial solutions to the matrix equation simultaneously when there's a free variable inside here. And that's going to happen when there is less than 2 pivots. So really all we have to do here is consider the matrix A itself. Let's do just that. If we take A, it's equal to 1, 5, 10, 0. We can row reduce this pretty quickly. multiply row 1 by -5, add to row 2 to get 0, -50. Now we have a pivot in column 1, we have a pivot in column 2, it's in an echelon form. So we can say, since there is no free variable, the matrix equation, AX equals to the 0 vector, has only the trivial solution. That part we just wrote down, that's the whole content of section 1.5, considering the homogeneous equation right here. Sometimes people don't write this down on paper, which is understandable, because we want to connect this thought, no free variable, or all columns are pivot columns, to the thought that this is now what we have. V1, V2 is linearly independent. Because no free variable means we had only the trivial solution. Another way to say this is there is a pivot in every column. That deserves an exclamation mark and an underline, because we have to keep columns really straight in our mind versus rows, or this can really mix us up. If there's a pivot in every column, then there's no possibility of a free variable, and automatically we have linear independence. So that's the short of this one. But we kind of knew we were expecting linear independence because they simply weren't multiples of each other. And that is a good thought, if and only if you're dealing with specifically two vectors and two vectors alone. So this is the shortcut way we'll think about this when we're doing problems on a homework or maybe problems on exam. You didn't necessarily have to do any of this on the row reduction, but we did it once because, again, we're just trying to learn how this theorem works or this definition works. So this is a great theorem, but it only works for two vectors. So the moment we go to three vectors or more, we can't use this whatsoever, which is unfortunate. The trouble is, if you look at a set of three vectors, any pair of them might not be multiples of each other, but they're still linearly independent because one vector could be a linear combination of the other two. And that's the problem that we run into. So it starts to get more and more complicated. And this idea starts to pay off a lot better if we have three or more vectors. But any questions at all, folks, running through this one here or the theorem below? Okay, so when we look at this again later on in these notes, kind of summarizing all these methods, pretty much we'll just eyeball this and say they're not multiples of each other. By the theorem below, they're dependent if and only if they're multiples of each other. So we're looking at linearly independent vectors. If we did the same kind of geometric view on this one, calling this the x1 plane, this the x2 plane, plot v1, this goes 1, 1, 2, 3, 4, 5. I didn't make this easy on me. The span of v1 goes like this. Just imagine that's a straight line. And then the span of v2 goes like this. 1, 2, 3, 4, 5. It's the x2 axis, which is kind of tricky to plot. We'll just make it bold. So here's v1, here's v2, and this is span v2. And this is what linear independence looks like for specifically two vectors. You're looking at the span of two totally different sets. Whereas up here, span v1 is equal to span v2. They're the same exact set. Well, now we're going to move over to three vectors and more and see how those go and what the related theorems might be. There's a couple other interesting theorems that are going to help us along the way, but any questions at the moment? Okay, I believe the next example is not as bad as it might seem. Oh, maybe it is. It's a little bit different. We have three vectors. None of them are the zero vector, and we want to know if they are linearly independent. Taking the approach like we did before, we could just write down a vector equation, but a lot of people would rather just jump right into that matrix and see if there's a pivot in every column. So let's reuse that thought from the very last example. Let's define let A equal. I'm going to put the vectors in, and then I'm just going to rewrite it as a matrix, and then we'll row reduce it. But looking at these vectors, they're not all that convenient to put in the order you see them. And that's kind of intentional on this problem because it could happen in the homework as well. If you're just testing linear dependence versus dependence, we can put these vectors in the matrix in any order that's convenient to us. Sure, these are an index set of vectors, so their order is important when we go to operate on them, doing other things that might be applied with these vectors. But just for a test in independence and dependence, this might be the nicest vector to put in first because it would go -1, 3, 1, and we would have a pivot right here. We wouldn't have to do row swaps necessarily. So I want to put V3 in that position. Next most convenient one, maybe V1. It might be kind of a toss-up at this point. But I'll put V1 in the second column. So it's going to go here, 0, 2, 3. Then V2 is going to be the third column, 0, 0, -8. And this is not going to be cool any longer. We're going to do a row reduction on it. You didn't have to do it in this order. Any order you put this in is going to work, but sometimes row operations could get more involved just from the different set of order that you might put these in. Here, I'm going to just multiply row 1 by -1, force it to be 1, 0, 0. At the same time, with it as a -1, multiply by 3, add to the row below, and it'll go 0, 2, 0. Add this row 1 to row 3, and it becomes 0, 3, -8. So putting V3 in first just made it a little bit faster to run through. Over here, that's really effectively of 1 if you divide that by 2 into row 2. So this is now 1, 0, 0, 0, 1, 0, 0, 3, -8. Last operation, I'm only going for echelon form, putting a 0 in this position. So row 1 is 1, 0, 0, row 2 is 0, 1, 0. Multiply row 2 by -3, add to the row below. Really nothing spectacular happens because of the zeros on the left and the right. We just kill the 3 below. It's now a 0. And -8 copies. We now have a pivot here, here, and here. Let's make this comment feel more official by saying there's a pivot in every column. And that's pretty much answering the whole question for us. If there's a pivot in every column, this means AX equals the 0 vector has only the trivial solution. Because there can no longer be a free variable if every single column is a pivot column. So this is the major thought that we really want to connect. If there's a pivot in every column, this means V1, V2, V3 is linearly independent. And pretty much the problem is done right at that spot. We never even augmented this with the 0 vector. All we need to do is see what's going on with the columns of the matrix A itself. Want any questions, folks, running through this one? Okay, so far we have really important information when there's a pivot in every column. At the same time, we have really important information when there's a pivot in every row. Here is the reminder from section 1.4. If we have an n by n matrix and we have a pivot position in every row, all these statements are logically equivalent. In particular, the columns in the matrix A will span Rm. That's what's going on here. There's a pivot in every row, so the columns of our matrix A span R3. Simultaneously a pivot in every column meant we have linear independent columns. So think pivots in columns is about independence, pivots in rows is about spanning. We'll remind ourselves about those thoughts a lot throughout this course, particularly in chapter 2 as well. So example 3 is just a glorified row reduction problem. Again, this is stuff we could have done in sections 1.1, 1.2, 1.3. The only difference is we have like 5 times the vocabulary now, and that's what makes linear algebra a little tough. I'd say a good way to study the subject is occasionally just go back to chapter 1 and reread it, maybe skim through it. Particular attention to the definitions really helps connect all these thoughts. There's a lot to put together. So here's the idea that we kind of went through on example 3. The columns of a matrix A are linearly independent if and only if x equals 0 has the trivial solution. But then x equals 0 has only the trivial solution. This occurs when A has a pivot in every column. So same thought as before. I guess example 4 is entirely new, right? It's the same kind of problem. Only difference is we might be thinking of this definition now. So another set of row reduction. Let's try this out again, see how it goes. Let's just launch into the row reduction on this step. It's already written down here. I'll copy in 1, 2, 4. Multiply row 1 by -2, add to row 2 to get 0, -3, -8 minus 1, so -9. Multiply row 1 by -4, add to row 3 to get 0. Let's see, that's going to be -8, so -9 here, -16. Multiplying this by 4 plus 1, so -15. Row reduction's nearly done. Let's go 1, 2, 4. I'll multiply or divide this row by -3. So 0, 1, 3. Let's divide this row by maybe +3. Yeah. Oh, let me take another look. So middle entry, this one right here. Oh, we multiplied by -4, so -8 plus 3. Yeah, -5. Thanks for spotting that. That's going to totally change the conclusion on this one. I was going to get independence or something and some nasty numbers. Thanks for the fix on that one. So now if we divide by -5, the better number, we get 0. Actually, let's divide by +5 to go along with the related comment last class. This makes visualizing the next step a little nicer. Same difference though, we're going to get the same conclusion. Divide by +5 and you'll get -1, -3, and then we're just going to fully add row 2 to row 3. So this becomes 1, 2, 4, 0, 1, 3, 0, 0, 0. This time only pivot 1, or excuse me, column 1 and column 2 are pivot columns. Column 3 is a non-pivot column. That means we're totally done. By this theorem and the add-on comment, we can now say, since A has 3 columns and only 2 pivots, we wouldn't say the matrix A is linearly independent. We're talking about the specific columns. These 3 different column vectors together are linearly independent. So a little bit more writing, we'll say the columns of A are linearly independent. And we did it, folks. This is the conclusion on this one. Row reduction kind of reveals everything we might want to know about linear independence, as well as spanning. This matrix A's columns cannot span all of R3 because there's not a pivot in every single row. But the underlying question was about independence. Because it's a 3 by 3 matrix, if it's not spanning, they're also not linearly independent. And that's an interesting thought in its own right. Spanning independents go together if you have the same rows as you have the same columns. We'll later call this special class of matrices square. So that's a square matrix. And the really big theorem that we previewed, that's like the extension of this one, only works for square matrices. So theorem 4 is pretty much always going to be important when your matrix is not square. Maybe it's 2 by 5, for example. So another row reduction, pretty much just extra practice, but it's good to see one where it's linearly independent, one is where it's linearly, hang on, let me try that statement again. We should have said linearly dependent. Sorry about that mistake there. The columns of A are linearly dependent because if there is a non-pivot column here, AX equals 0, has a non-trivial solution. Sorry if you were looking at that and scratching your head. I think I was just trying to write too fast or something. But does that make sense for linear dependence on this one? Let's bring in the definition just so for some reassurance on that. Okay, so that's a good moment to reflect on. Definitely don't do it as I did. We always want to keep really strong, stuck together in our minds that having a linear dependent set of columns means a non-trivial solution exists. Linear independence, like the one above, is when there is only the trivial solution. Pretty much we can just see at a glance what's going on just by the pivots, but make sure the conclusion's right. Well, let's take a look at a couple more ideas. We're nearly at the end of these notes. Next idea is what happens when you have kind of a weird set of vectors. There's 3 vectors taken all together. We want to know if this set is linearly independent. It's kind of the same problem as before, but this is a problem you might have noticed. You don't necessarily need to do any row reduction. In fact, this problem really connects well with what we were talking about in section 1.5. Section 1.5 had a really interesting example or idea that said if you're considering the homogeneous equation x equals 0, and if you're ever in this situation, if there are more columns than there are rows, then there's automatically non-trivial solutions. I regret that color coding. That should have been green, because if there are non-trivial solutions, that would mean linear dependence. So when we put together these 3 vectors here, we said that there is a non-trivial solution immediately, and we didn't have to do any row reduction whatsoever. There's at most 2 pivots, so one column is going to be a non-pivot column. Same idea here. There's really doesn't take a lot of computation. If we were to explain our answer, we might say, let A equal V1, V2, V3, which is 1, 7, negative 1.73, negative 1, 1. Next thing we might say, without doing really any analysis on this, is A has at most 2 pivots. And so AX equals a 0 vector has a non-trivial solution. That means our work is done with this. The moment you know there's a non-trivial solution, because one column is a non-pivot column, we conclude immediately, therefore, V1, V2, V3 is linearly dependent. That's kind of nice. That's the value of a good set of ideas, good set of theorems. It just makes computation really fast. In fact, we did 0 computation on this at all. It doesn't matter whatsoever what these entries are. Sure, if it was all zeros, then yeah, it's automatically linearly dependent. The 0 vector's in there. But for random numbers like these, we don't have to think too hard. If you did this problem on exam 2 with row reduction, you're not going to get docked points. But exam 2 could be longer than really intended when some of these problems are meant to be thought through the lens of these kind of ideas or these kind of theorems like this one above from section 1.4. Let's leave that there just for a moment. Any questions so far, folks, getting through this one? Okay, so that continues to be a really nice theorem from the last section. 1.5 was a weird section because we really didn't know what we were going for. It was just considering vector equations and matrix equations set equal to 0. And this was the idea. We're trying to determine what linear independence is, what linear dependence is. And finally, let's see here. That's the theorem that goes along with the last problem. Really, theorem 8 is just a redo of the prior theorem in the last section 1.4. If you have more vectors than entries per vector, you have automatic linear dependence. So here we had 3 vectors, but only 2 entries per vector. We didn't necessarily have to even write this down. We can just observe linear dependence through theorem 8. Example 6 is just a whole nother idea to take a look into. The thing that's interesting about example 6 is we have the 0 vector in this set. Any guesses if this is independent or dependent versus that 0 vector? Let me say that better. Any guesses in the class on whether this is a linearly independent set or a dependent set based on the 0 vector being inside the set? What would you all say to this one? Yeah, I agree. In the class, that this determination is dependent. Looks like we have a full agreement on that. And a really fast way to see it, write down the matrix equation again. If you go, say like this, I'm going to put in x1, x2, x3, x1, b1 plus x2, b2 plus x3, b3, set equal to the 0 vector. We'll just observe that that vector right there is v3, and we automatically have a non-trivial solution. A non-trivial solution. There's infinitely many, but here's one. Is x equals, you don't have to write this part, but just to be real specific with the way we're writing that solution as a column vector, I have to put 0 here and here. Maybe not necessarily that I have to, but just for ease of computation. I don't know if they're multiples of each other. Doesn't really look like it. But to get a non-trivial solution, I'll just put in a 1, anything non-zero. That does it. The 0 vector allowed us to put a non-zero entry right here. So our conclusion is, therefore, v1, v2, v3 is linearly dependent. This is a pretty weird section the more you look at it, because it looks like we're writing down more words than we're actually doing like math, like row reduction kind of stuff. This is more about the words than the numbers in a very real sense. And theorem 9 is really just the whole punchline to this. Let me move that around a little bit better. The moment you see a 0 vector in your set, even if the first vectors are linearly independent, doesn't matter. Your set is automatically dependent just because of the presence of the 0 vector. So that's another nice theorem to have in our toolkit. We can just tell at a glance if our list of vectors has the 0 vector, the overall conclusion of dependence. So lots of theorems so far. Let's see. What we want to do is just see what a typical problem like this is going to look like. The next example is pretty much what you're going to see as a homework problem. You'll have a bunch of vectors that are given to you, and the instructions are interesting. It's going to say, determine by inspection. The author's trying to tell you, you don't have to row reduce on these. I won't dock you points because a correct method is a correct method, but the idea is there's powerful theorems in the background, like theorem 9, theorem 8 is a really nice one. That's going to eliminate the need to do any row reduction whatsoever. So think about the theorems when you answer these questions. Example 7 is going to come back as an exam 2 question as well. I won't ask you to let's see, briefly explain your answers because I'd be making the exam pretty long. But doing it in the homework is going to connect all these ideas together. So let's start this off. First set of vectors is just containing one vector itself. Anyone see what the conclusion should be for this one? Would this be independent or dependent as a set of one vector? Absolutely, this is an independent vector. Independent because it said briefly explain your answer. That means, again, you don't have to do row reduction. You just need to say something quick. Anyone know the punchline on why independent? Exactly, yeah. If you took x times this set to the zero vector, you have to force your scalar to be zero on this one. There's no way to get around it. So you could say because x1 times 178 equals 0, 0, 0 forces x1 equal to 0. In other words, there's only the trivial solution. I like that explanation. It gets right at the heart of the definition. Other people might have had different things in mind. You might have just said, imagining this is a homework question, independent because it's not the zero vector. And that would have been fine as well. You're directly citing a theorem in that way. And this is directly going through the core definition. Both great answers. The idea is you didn't have to row reduce this one whatsoever to get this foregone conclusion. So we'll try out a couple more just to see how all these go. Next one goes, well, it's two vectors. The trick when it comes to two vectors is to decide, are they multiples of each other? And it's easy to kind of lose our way on this because if I multiply entry 3 by 2, I get the 12. Multiply entry 2 by 2, we just got mixed up there, we'll get the negative 6. So it seems if you scale this by 2, you're getting the right stuff, except you have something that goes 0, 1, it's all broken. Scale by anything, and you'll get 0, resulting in 0 here. So this is automatically telling you right at a glance, linearly independent. Let me match up the color here. Linearly independent. The quick answer on this is because they are not multiples of each other. You could say not non-zero multiples of each other to be hyper-specific, but usually that's implied when you say it this way. Then that does the job. There's some danger with this thought, though. This idea, they are not multiples of each other, only works for sets of two vectors. So watch out for that idea there. That makes it a little bit restrictive in how nice this is. Any questions, folks, on part B? Okay, part C we kind of just looked at, right, on example 6. The key feature about this is it's a more complicated set of vectors because we have 3 going on. But the moment you see the 0 vector, the conclusion is foregone. This is linearly dependent immediately when this is entering the set. So that's all we would have to say, linearly dependent due to the 0 vector. So really, it's kind of just a tour of all the theorems that we've seen so far in these notes. Here's a kind of unusual situation. Anyone recall what the conclusion should be for part D? Is this independence or dependence? Yeah, absolutely. Good call on this one. We can say linearly dependent. The way we analyzed this one was we put it in a matrix and we observed there's at most 2 pivots. So there's going to be a free variable on the homogeneous equation. But another way to say all of this is you could say linearly dependent, citing the idea in the theorem. There are more vectors, 3 of them, than entries per vector. There's only 2 entries per vector. That does the job. If you have more vectors than entries, automatic dependence. Well, any questions so far, folks? Okay, I don't have a tough one on this list where you would use row reduction, but those are kind of the harder problems we're looking into. I think something like example 4, maybe 3 or 4. This one, though, we have to watch out for this issue where a 0 entry becomes a non-zero entry. But when 0 entries match up, then anything can happen on this one. But you might have noticed if you scale vector 1 by 10, you would get negative 30 and you would get 60. That means it's different than part B. Those are independent because they're not multiples. These are multiples of each other, so they are automatically linearly dependent. So all we need to say is linearly dependent. They are multiples of each other. Some people wouldn't even write in this comment. They might just say, label this as V1, V2, and the explanation could just be 10 times V1 equals V2. This is what the author referred to as the so-called dependence relation. It's a vector equation involving V1, V2 that we could make into a homogeneous equation by subtracting V2, and it would have a non-trivial solution, 10, negative 1. But that's the tour of really quick theorems that we were looking into. For everything else, if this wasn't a 0 vector, maybe it was 1, 5, 4, then we're just doing some row reduction and seeing if all columns are pivot columns. If so, we'd call it linearly independent. But any questions at all, folks, with the quick run through of these theorems? Okay, these theorems are great because it works really fast if we're looking at vectors in R3, R2, or R4, and so on. But when we go back to chapter 4, we're going to discover that this definition just becomes relevant all over again, that all of our theorems are going to break if instead of Rn, we have a space of polynomials or maybe a set of cosine sine functions that got spanned into another vector space. That could be the solution set to some random differential equation. So those are other vector spaces that we need to consider. So chapter 4 gets a little bit more abstract, but then we'll just revisit this definition pretty much verbatim the way we see it right here on paper. I have a couple more side problems to take a look at in this section before we go off to the next one. And here we're just trying to tie together some old ideas that we've been referring to quite a lot. The differences between having a pivot in every column versus having a pivot in every row. So this is kind of a vague question, but it's meant to be just something we're connecting in the notes. Example 8 says, let A be an n by n matrix. We mentioned that's pretty special. We have a square matrix, is another way said. So it's square. We're going to also assume that the equation Ax equals b has a solution for every vector b in Rn. So the matrix equation is consistent no matter what you put in for the right-hand side of the original equations. Our target is to explain why the columns of A must be linearly independent. And that's an interesting connection, right? We're connecting solving a matrix equation with linear independence. The thing that connects all of these thoughts now is the fact that we have a square matrix, and all the way back into section 1.4, theorem number 4 is the one that supports us. So let's just screenshot it in. It's the star of the show. The theorem says the matrix A is m by n, but that includes the case it's n by n. M and n had no constraints. This is just allowing them to be non-equal, and this theorem still works. It will work if they are equal, n by n. So theorem 4 still works for us. And when we were saying this part right here, trying to decide on what part to color code, let's just use a marker here. Ax equals b has a solution for every vector b. That was just referring to part A. Ax equals b is always consistent. It always has a solution. So here's the dots that we can now connect. Since Ax equals b has a solution for all b in Rn, the n is unspecified. It could be 2, 3, 5, a million. This idea is still going to work just as before. But since Ax equals b has a solution for all b in Rn, all of these statements are true, but we want to connect this with there being a pivot now in every row. So this implies immediately A has a pivot in every row. So that's our next implication. But this matrix was special. The number of rows equals the number of columns. So if you have a pivot in every row, n pivots, you have a pivot in every column. So the next implication goes, A has a pivot in every column since A is n by n. And I did miss one thing I want to say here, just for the sake of clarity. A has a pivot in every row. Let me say it this way. By theorem 4 of chapter 1. I said this in a kind of weird way, and the reason I said theorem 4 of chapter 1 is something that's kind of annoying about this textbook. When we go to chapter 2, theorem 4 is a different theorem. So once we get to the next chapters, we need to specify which chapter the theorem is relative to. Other books might have went 4.1 to say theorem 4 of chapter 1, but we just have to write it out. So I'll try to always be specific so you can actually look it up and know which theorem 4 we're even talking about. So A has a pivot in every column since it was a square matrix. This implies, well, all columns in the matrix A are a pivot column. And so automatically we have the conclusion A is linearly independent. Again, it's a strange math problem because we wrote down a number here and here, but that was just citing theorems in chapters. This was just purely connected glue amongst all of our theorems and definitions we've been looking at so far. But does it make sense how we got from the start here to our end conclusion? Okay, well, we did it, folks. That's the linear independence section. Linear algebra is kind of weird because when you're doing stuff like this, feels like a weird kind of math. It's not like a calculus class or even a differential equations class where it just seems like you're doing computation after computation, solving differential equation after differential equation. This stuff is weird. To me, when I first took linear algebra, it just reminded me of taking like biology 101 and learning these complicated charts like how photosynthesis works and stuff like that. You're just connecting ideas together and definitions and principles. That's about what this problem is all about. It's not going to be every problem in linear algebra, but every now and then, this is what the math actually looks like. So we concluded our work on linear independence. To take just another quick view of how all this fits together, it's good to have an overview with all these strange definitions. We're actually going for something here, and we're trying to get down to the basis of a vector space so we can say what the dimension of a vector space would be altogether. We have the two key ingredients. So this was the huge objectives of chapter 1. We know what spanning is. We know theorems that support it. Having a pivot in every row means the columns of a matrix spans a space. And we know what linear independence is. Having a pivot in every column of a matrix means those columns are linearly independent. Taken both together, a set of vectors that both spans a vector space and is linearly independent is what we mean by a basis. So if you want to review these ideas, sections 1.1 all the way through 1.7 are good to review. And if you like seeing it in a different way, that's the purpose of these examples here, or these videos here and here, connecting some of these ideas. Next thing we're going to do is sections 1.8, 1.9, kind of a recapture of everything we've done from 1.1 to 1.7, but we're defining something new. We're going to finally say what we mean by a linear transformation. And this is a special spot in linear algebra because if experts in the field were to say in one sentence, what is linear algebra, it would probably capture this in spirit. What linear algebra is really all about is not systems of linear equations like we saw up here. That's just us getting started. Linear algebra is really all about the linear transformations between vector spaces. We'll see a lot of their interesting uses and some pretty profound thoughts that come out in chapter 2 and chapters 4, ideas about something called isomorphisms, meaning same space, and another look at the use of linear transformations. Take a look at this application video here. It's just kind of nice to see what matrices are doing in computer graphics. So here's how the definition starts. All we're doing is defining a function. And all of our work in these prior sections were like us talking about the domain and the codomain. What we really like to talk about is the actual function itself. So we can call these functions, sometimes we call them mappings. Linear algebra, we often call them transformations. A transformation is a function or mapping T, quite like lowercase f when you define a function, that maps from one vector space Rn into another one, Rm. The way we sometimes write this out is through a quick arrow diagram. This whole statement, T is a transformation mapping Rn into Rm, can be paraphrased in symbols just by writing this. So this is a common thing you might have seen in other contexts as well. And it becomes more common in linear algebra when we're dealing with the transformations. So it's a rule that assigns every vector x in Rn a new vector t of x, so we're using function notation, in Rm. So Rn, where we started here, is the domain. The target space, where everything is mapped into, is called the codomain. We use this notation a lot to indicate what the domain is and what the codomain is. And once again, this feels redundant, but these are a lot of words that get mentioned in the reading and in the exercises. For every vector x in Rn, the domain space, t of x is the image of x under the action of t. It's just a value in the range. The range is a set of all outputs. That's a subset of the codomain. Sometimes the range is exactly the codomain. Sometimes there's vectors inside the codomain that you can't map to from T. So there are non-range elements potentially, depending on the mapping. That's a lot of definitions all at once. Part of the goal of section 1.8, it's the introduction to these, is just to get used to these terminologies. Section 1.9 is going to introduce us to a lot of theorems about the linear transformations. And we still haven't even defined what we mean by linear. This definition is just simply for transformations itself. Well, while we're absorbing this, any questions at the moment? Okay, so transformations like these, in a calculus setting, they might just be written like this one. T is going to map from R2 into R3. So it's a function that takes a vector, and it's vector valued because it's going to output a vector with 3 entries. Kind of a weird one because our second entry is always 0, but you know what? That qualifies for this kind of function. We usually write it this way in linear algebra because we like to think of our vectors as column vectors. And sometimes even the author writes it this way, sideways. So we'll see it both ways in the reading and in the exercises. So I'll write it occasionally both ways as well in the notes, just to emphasize this different notation. Instructions are just asking, what is the image of X? It's the column vector 1, 2. Checking. That makes sense. It came from the domain. So we want to know the image of X under the mapping T. And in this context, it's not a bad problem because we'll see how it goes. But it's a tough problem if you do this on the homework exercise because you had to know when it says image of X, you're just doing T of X. And it can be an even tougher question in an exam setting. Now you're not necessarily knowing the context, you're in 1.8. So again, part of the objective on this is really just the vocabulary. When you hear image of X under the mapping T, just think all you're doing is T of X. And that's a great way to think about it. Well, before we do the image, there's a lot of ways to write out these linear transformations. Again, this section is pretty similar to what we've done already before. We just have extra terminology and extra machinery connected with these thoughts. If you really look at T of X carefully, it could have been written this way, T of X1, X2. That's because this X is really a vector coming out of R2. It has two entries and maps to this 2x1 minus x2, 0, 5x2. But this column vector is really just the result of a linear transformation. Think of the sort of skills that we practiced when we wrote things in parametric vector form. We can decompose the vector additions and scalar multiplications by rewriting x1 times a column vector, pull all x1 coefficients, and they go 2, 0, 0. Plus x2 times a new column vector, pull x2 coefficients, they are -1, 0, 5. So we have a linear combination out of nowhere. But even more interesting, a linear combination is the result of a matrix times a vector. That's our definition of a matrix times a vector. So this whole thing can also be rewritten as 2, 0, 0, -1, 0, 5 times x1, x2. All this really is a matrix A times a column vector x. We just happen to have a specific column vector. So we, if we wanted to, can compute this whole thing by going, it's equal to T of 1, 2. This always seems kind of funny, I should mention, putting a parentheses around a bracket. Some people get annoyed by that and they just write it this way, which is completely valid. I'm putting in the parenthesis just to remind us this is honest function notation because the mapping T is just a particular kind of function. This becomes 2, 0, 0, -1, 0, 5, multiplying 1, 2. You could have done this differently by saying x1 is 1, you're plugging 1 here, x2 is 2, you're plugging 2 here and here, just giving the output. But this is a pretty interesting kind of view as well. So far a transformation like this was just a matrix times a vector. This doesn't always work out for every transformation. You might have noticed in calculus, for example, or just connecting the thoughts from section 1.1 over here, if one of these rows doesn't quite look linear, say it's a x2 times x1, we've got a really big problem. That's why in section 1.1, let's go down memory lane just for a moment. Forget Word documents, take a moment. We were pretty concerned when we see something like this. The equation is no longer linear. We're pretty concerned when we see things like, say, what else was a problem? Cosine x1. That's equally bad as x2 times x3. Sure, there's no equation here. This is just a function. If you have things multiplied here, our transformation is nonlinear, and this is a hard one to study. It means there was no matrix here whatsoever. So lucky us, it happens to be just linear type stuff right here, meaning our transformation T was linear, and that's the reason why we got this matrix. This matrix is so special, it even has a name. This is called the standard matrix of T. It turns out our transformation is just what we've done all before in section, I believe that was 1.4, taking a matrix times a vector. First thing we probably want to check is, can we do it? It's size 3 by 2 here. This is size 2 by 1. The inner dimensions match. The number of columns is the same as the number of entries. So yeah, we can multiply this out. I didn't quite make that tall enough. I think I was trying to, but then just messed up a little bit. This has to be size 3 by 1 because there was 3 rows and just 1 column on the vector there. So we take the entry 2 times 1 plus the entry -1 times 2 and get a 0 out. Take 0, zeros here, multiply and add, we get 0 again. 0 times 1 for 0, plus 5 times 2 for 10. That's just a redo of the section 1.4 topic. And that's the image under the transformation T. So we did it, folks. So far, transformations looks like just glorified matrix multiplication times a column vector. But again, that's because there was nothing weird going on like x2, x1. That would have broken everything on this. Any questions at the moment doing this transformation? Okay, so this is what the work looks like so far. It's kind of a review of content. Here's where the new information comes in. I cited a theorem from section 1.4 that we just never used. We didn't have a cause to use this theorem. But the theorem from section 1.4 was telling us if we have an m by n matrix, u and v are 2 vectors in Rn and some random scalar c, there's a couple of nice algebraic properties. Matrix multiplication distributes across vector addition, so that's kind of cool in a way. And this is a kind of commutativity property. Matrix multiplication, when we scale a column vector, can be done in 2 ways. Either scale u, then do the matrix multiplication, or you can just do the matrix multiplication first and scale the result by c. So that's 2 interesting properties that we really didn't have much to do with when we were in section 1.4. But now here's where they really matter. This is where we finally define linear transformations. Transformations T are linear if they do just 2 things. Take any vector u and v in the domain T. The mapping T applied to u plus v is the same as the outputs T of u plus T of v. This doesn't seem like much when you look at it on first glance, but it's really saying a lot. This is an operation preserving property. Scalar addition in the domain is preserved when we do scalar addition in the codomain. And in a real sense, that's pretty weird. Functions typically don't do that. Think back in algebra, like say sine x plus y. If you try to do the same thing, you get a pretty weird result out on this thing. My trigonometry is a little bit rusty, but I think this goes sine x cosine y plus cosine x sine y, the addition formula. Might have to double check that for me. So this is a property that is totally different from this one over here. It's just a reminder that functions, even this property alone, is pretty weird. You don't often have the ability to do something like that. Let's remove that for the notes so it's not a huge distraction if you come back here. And at the same time, the operation of scalar multiplication is preserved by T. This is also operation preserving in the sense that you can either scale U, then apply the mapping T, or you can apply the mapping T first and then just scale it in the codomain. Wherever you do the scaling doesn't matter. Same idea here, vector addition, do it in the codomain or in the domain, and you get the same exact result. Because of these two properties, these are called operation preserving properties. Somehow, some way, the linear transformation T allows these, but notice the parallelism here. Same idea with vector addition here when you multiply by a matrix. It's literally the same property, swap A with T. Same idea here in property B, swap A with T, and you have the same property down here. So these two random facts from section 1.4 happen to be extremely relevant every time that you can write your matrix your transformation T as a matrix times a column vector. It turns out if you're mapping from Rn to Rm, every single transformation that is linear will have this matrix here, which we call the standard matrix. And that's a really remarkable fact. It breaks down, unfortunately, it breaks down in a major way if this is anything but Rn. So if this is a more exotic vector space, there is no standard matrix A necessarily, and so we have a problem. But these are the ones that we've been studying all along in the course. We'll study them quite a lot more. And so this is a major idea we'll take a look at when we come back to this part of the notes next class. That any transformation T, if you can write it this way, it's automatically going to be linear because of the properties above. So part of our goal is to be practice with what it means for transformations to be linear, finding that matrix A and working with it. And some of the challenging problems we're going to see in this section of notes and in the homework as well is when we take something like, say, this and explain why it's nonlinear. Sure, that's the problem, but we need to work it through the definition and really say once and for all, why is that nonlinear? So that's going to be the tough one in the notes. Well, I don't think we have a lot of time to make any serious headway into this problem, but I want to at least introduce us to the definition. We'll take a look at this and work through it in our next class. But any questions at all, folks, before we call it a day?
Are there situations where one of those properties will work but one won't?
Yeah, absolutely. We're going to have that in our notes as well. And I think in an exercise, one will work. It might be scalar addition is preserved, but something goes wrong down here or vice versa. Yeah, they can break in parts. Other questions so far? Okay, well, have a great afternoon, folks. We'll come back to here when we come back next class. And here's the spec for you. Yep, preview. Oh, that includes your homework. So it's your entire course to date.
Oh, yeah, course.